before we jump into this, I would like to go over a quick visual example of what a system of equations is, our options for what our answers might possibly look like, and then we'll jump into how we solve them. So a system of equations, for us, we'll be looking at 2x2 systems of equations. System just means that we have more than one equation. For us, we'll be looking at 2 equations. So we'll be given 2 linear equations, and our goal is to find out what points satisfy both of the equations, or what points are on both of the lines. Okay? So we're trying to figure out what points they share in common. This can be simplified into 3 different cases. All right. Let's quickly think about, if we have 2 lines, let's think about the graphs. What can the graphs of 2 lines possibly look like? We can have 2 lines, one that increases, one decreases, both of them increasing. Most of the time, our 2 lines will end up intersecting at some point. So that'll be case 1. We can have 2 lines that intersect. Boom, there's one line. Boom, there's the other line. And then ta-da, in the middle there, we have a point of intersection. Okay, so the first case is that the lines intersect at one point, and then at one point would tell us what X and Y, or what ordered pair, or what point these 2 lines share in common. They only share that one point. This is an example of where we have a system of equations that has one solution. The solution is the point where these 2 lines intersect. Remember, the goal of this is to take our 2 lines and figure out what points the lines share. Boom, if they intersect at one point, they only share that one point. Boom, that's our solution. So case 1 is an example of where we might have one solution. I'll write it up here. One solution. That's when our graphs intersect at one point. All right, then case 2 is kind of the opposite of this. If our graphs have different slopes, they're gonna end up intersecting somewhere. But if our graphs have the same slope, but different y-intercepts, they never intersect. We end up with parallel lines. So if we if we have 2 graphs, or 2 lines, I should say, with the same slope and different y-intercepts, we have parallel lines. And then what points do 2 parallel lines have in common? They don't have any points in common. They're parallel. Parallel lines do not intersect. So they have no points in common. This would be a case where there is no solution. No solution because they have no common points. All right, and then our third case, this one's a little tricky to draw. But sometimes we'll be given 2 equations, and when we write them in slope-intercept form, or when we graph them, they actually end up having the same graph. An example of something like this would be, I don't know, let's go -x plus y equals 4, and -2x plus 2y equals 8. These linear equations look different, but when we write them both in slope-intercept form, we get the exact same thing. It turns out the second line is just the first line multiplied by 2. So they're not 2 unique lines. They're actually just the same line. And when we graph them, graph the first line, we get that. When we graph the second line, it's literally right on top. They're the same exact line. I'm going to try to draw these together. All right. So in this case, where the 2 lines actually have the same graph, the lines are on top of each other. So that means that every point on the blue line is also on the red line. So what points do they share in common? All of them, every single point. So this would be a case where we say we have infinitely many solutions. And a solution would be like literally any point on the line. So you pick an X, plug it into the equation, find the Y, boom, that ordered pair would be a solution. Because every point on the blue line is also a point on the red line. So that's our third case. We have infinitely many solutions. All right, these are the only options. If your two lines have different slopes, they're going to intersect at some point. That intersection point is the solution. If your lines are parallel, they're never going to intersect. So they have the same slope, but different y-intercepts. They never intersect, so there's no solution. Or sometimes you might end up with the exact same line. They have the same slope and the same y-intercept, so they're the same line, and every point on the line gives you a solution. Okay? We want to find, if we're given a system, which one of these cases we have, and then if we have like one solution, figure out what the intersection point is. If there's no solution, show that there's no solution. And if there are infinitely many solutions, we need to state that, and then sometimes give an example of one or two solutions. All right, doing this graphically is very, very easy. We pretty much just did it. You will take whatever lines you're given, graph them, see what case you have. If they intersect, find the intersection point, that's your answer. If they don't intersect, then there's no solution. Most of the time, our problems will intersect, but of course, we also have some no solution and infinitely many solution examples as well. For problem 1, this is a guided example that we're going to solve numerically and graphically, and then we're going to get into our algebraic solutions. Lucian has been offered 2 options for his annual salary as a personal trainer at the gym. Option A would pay him $25,000 plus $15 for each training session, and option B pays him $10,000 plus $40 for each training session. So just looking at these, we can see that it's hard to kind of decide which one to do, right? If you really think about it. So obviously the first option starts off with much more money. We're starting off with $25,000 versus the second option, which starts off with $10,000. But with the first option, you only get $15 for each training session. But for the second option, option B, you get $40 for each training session. So to determine which of these would be, the most ideal job or which job offer he should take, it'll kind of depend on the number of training sessions, I guess. And it would help us to write a linear equation to represent each situation and then to graph the lines to see which one is above the other, okay? We're told Lucian's salary is a function of the number of training sessions conducted. N represents the number of training sessions. And S of A and S of B represents the outputs. So write a function that represents Lucian's salary for each position. I'll try to color code this. For option A, S sub A is going to be equal to $15 times N, so $15 for each training session, plus that $25,000 that we get in the beginning. For S of B, option B, we have 40N plus $10,000 that we start off with. All right, we're asked to then complete the table to determine how much the salary would be for these various different years. You can do this in your graphing calculator. Yeah, let's go ahead and do it in our graphing calculator because part C asks us to interpret this also, and we're going to have to use the graphing calculator for parts D also. So we'll use the graphing calculator to fill in this table for part B. Part D says how many training sessions must he conduct for the salaries to be equal. So we'll look at the table to figure that out, and then we'll look at the graph for part D, okay? Okay, you should be able to see our graphing calculator. Couple of things. One, we are no longer doing regression problems. Sometimes if you leave the stat plots on, you'll get an error when you go to graph other things. So we're going to turn our stat plots off. I'm just going to press 4 to turn them off. You only need to have them on when you're doing regression. You can have them off for everything else. Okay, then under y equals, I'm going to clear out the old equation and put in our two new equations that we had. So the first one was 15n or x plus 25,000. The second one was 40n or x plus 10,000. So we have our two equations in. We want to fill in our table. We were given the inputs. So we're going to let the table set, the independent variable, be on ask, and we'll input the numbers that were given to us in the table. It was 0 to 800 going up by hundreds. We can also let the table do it for us. There are a few different ways you can do this. It's probably easiest to just go ahead and type them in really quickly. So under table, let's type in the numbers that we were given for the inputs. 0, 100, 200, 300, 400, 500, 600, 700, and 800. Right. Once we have this in, you want to write this into your table in the book for problem B. So fill in the gaps. Some of it was already given. A lot of them were missing. All right. Now, we were asked to look at this table and then determine where or for what number of sessions will the salary be equal? 600. Yeah. So we see here when, forgot this guy's name, Charlie, Billy, Zach, I don't know. When this person, Lucian, that was his name, Lucian, does 600 sessions, and both jobs he'll end up getting paid for $34,000. But let's look at what's happening before and after that. So if he does less than 600 sessions, which job would give the higher salary? A, right? So if you look here, before 600, all of the blue values are greater than the Y values. So if he's going to end up doing less than 600 sessions, he should, which sounds like a lot, but if he's doing less than 600 sessions, then he should definitely do or take job A, because that would end up paying more. But if he's doing more than 600 sessions, which job pays more? The second one, job B, okay? So at first, when we think about this, job A is gonna pay more, and then at 600 sessions, they actually pay exactly the same, and then job B ends up taking over. Job B earns more. All right, we have the table here. We've kind of analyzed and thought about this a little bit. Next, we're going to look at the graphs for this function. For part D in our books, we're told to graph this with the window 0, 1,000, 100, and then 10,000, 50,000, 1,000. So let's change our window. For X min, we want 0. For X max, 1,000. 0, 1,000. And then for the scale, 100. For Y min, 10,000. Y max, 50,000. And then the scale was 1,000. All right. And then we'll press the graph button to see the graph of these two lines together. Here we go. So we can see both of the lines. At first, job A, the blue line is above the red line. So we see that, okay, the blue line or job A is better. Then at this intersection point, this is going to be the point 600, 34,000. That's what we saw from the table. At 634,000, the jobs are equal. The salary, I'm sorry, is equal. And then after that, job B takes over. All right, so what we've done here, where we're looking at the two graphs and we find that intersection point, that's solving graphically for a system. Also, we knew what the point was based on our table, but let's find that using the calculator. So how would we find this intersection point? Just by looking at the graph. Follow these steps. You want to press second, and then you want to press the trace button. This will get you to the calculate feature. So second and then calculate, and under calculate, you have lots of different options. We want to find the intersect. That's where two lines cross, or the two lines cross. So find the intersect, click enter. And then the calculator is going to require you to hit enter 3 times. click enter on each line, and then hit enter for it to give you the answer. So notice it says first curve, question mark, enter. Second curve, question mark, enter. And then guess, yes, guess, enter. Hit enter 3 times, and it'll give you the intersection point. All right, so this is solving graphically, finding the intersection point of the 2 lines. If we go back to our table, we also solved numerically, looking at the table and figuring out for what input you have the same output. That would be solving numerically. So solving numerically, we see that the solution is, what was the solution? Same thing, 600, 34,000. And the next thing we need to talk about is how to solve these things algebraically, which will take a few more steps. Next, we're going to do some algebraic solutions. So first, again, our solution to the system of equations is going to be an ordered pair, x comma y. For that last one, the solution for Lucian's situation, when will the jobs pay the same amount, is the ordered pair 600, 34,000. So we're looking for ordered pairs here. We know how to find them graphically and numerically. Jump into our methods for solving algebraically. We have two methods that we use. The first one is called the method of substitution. Basically, you're going to substitute one of the lines into the other line. So you have 2 equations. You take your first equation, solve for one of the variables, either one, whichever one's easiest. And then you take what you get and substitute that into the second equation. And then that will give you a linear equation with just one variable. Instead of having x's and y's, we'll have just y's or just x's. And then you can solve for x. And once you solve for one of the variables, so let's say we get x equals 5, then we can plug 5 in to the equations that were given and solve for the other variable. So the steps again. Solve for one of your variables in one of the equations, substitute what you get into the other equation, solve the resulting equation, and that'll give you your answer for one of the variables, either x or y. And then you use that and plug it into, again, the original equation to solve for the other variable. So if you solve for x, use the x to solve for y. If you solve for y, you'll use the y to solve for x. Then write your final answer as an ordered pair. All right, problem 3 has worked for us, so we're gonna skip that. I like to go to the ones where we do it ourselves. Problem 4 is asking us to solve a system graphically and numerically. We already talked about graphically and numerically. I want to focus on, it says solve by substitution and numerically. I was about to say, I want to focus on substitution. So we're going to solve this one using the substitution method. First thing, when we look at these 2 equations, one is written in standard form, the other is written in slope-intercept form. You have to ask yourself, can I easily solve for one of my variables from one of these equations? And when we look at it, yes, it's super easy. The second equation already has y solved for us, right? For the second equation, we have y equals 3x minus 2. That's easy. So we've isolated the y in the second equation. All right, where does the substitution come in? I usually call these equations 1 and 2, so I'll just make a note of it, 1, 2. So we can use y equals 3x minus 2 and substitute into equation 1. So since we're using the second equation, we're going to plug it into the other equation, the first equation. So we're going to take x plus y equals 6, and we're replacing the y with what we got in the second equation, 3x minus 2. So replace the y with 3x minus 2. That gives us x plus 3x minus 2 equals 6. Now, why is this nice? Before we had x plus y equals 6. We had 2 unknowns there. We can't solve that. Now we have x plus 3x minus 2 equals 6. It looks longer, but we only have one variable there. We only have x's. So now we can solve this for x. This gives us 4x minus 2 equals 6. Adding 2 to both sides would give us 4x equals 8. and then dividing both sides by 4 gives us x equals 2. All right, so x equals 2. You might be feeling like, okay, we're done. Previously, when we solved linear equations, we solved for x and we're done, that's it. However, this is a system. So remember, we need an ordered pair. We can't just stop at x, we also need to find y. All right, so we have used the second equation, substituted it into the first equation, and now we've solved for x. The next step, we can then use what we got here. So use x equals 2, and you can use either equation to find y. We can use equation 1 or equation 2, but it'll be easier to use equation 2. So from 2, y equals 3x minus 2, and we know x is 2. So that's y equals 3 times 2 minus 2, y equals 6 minus 2, so we get y is equal to 4. Then our final answer will be an ordered pair, x comma y. So it looks like we have, the solution is 2 comma 4. All right, if you were to solve this numerically in your graphing calculators, you would have to put both equations in slope-intercept form, put them in for y1 and y2, and then scroll down your table until you have both of the outputs being equal. Okay? For showing a numerical solution, like showing your work, you write down a few rows. So we can look at like x equals 1, x equals 2, and x equals 3. For y1, if x equals 1, y would be equal to 5. When x equals 2, y1 equals 4. And when x equals 3, I'm sorry, that should have been a 3. When x equals 3, y1 will be equal to 3. All right, and for y2, when x equals 1, y2 is equal to 1. When x equals 2, y2 is equal to 4. And when x equals 3, y3 is equal to 7, or y2 is equal to 7. So that's what the table would look like if you did it in your graphing calculator. You don't have to do it step by step like that. Use your graphing calculator when you solve numerically. And then you would just want to circle the row where you have the same output. And then x comma y will be your solution. All right. So for the rest of the problems we do, we're going to use algebraic solutions, or use algebra to find our solutions. We'll do a few more problems with solving using substitution, and then we're going to jump to our other method, which was solving using addition, a different technique. Any questions about problem 4 before we go to the you tries in problem 5? All right, so we try in problem 5. Are there multiple points? No, just this one. So for problem 5, when we look at these two equations, we have negative 2x plus y equals negative 11. And then x plus 3y is equal to 9. Remember, your first step is to try to solve for one of the variables in one of the equations. Usually you want to look for the variable that has a coefficient of 1. So for instance, in the first equation, y has a coefficient of 1. In the second equation, x has a coefficient of 1. So then you have to decide, do you want to solve for x or do you want to solve for y? It truly doesn't matter in this example. If you want to solve for y, use the first equation to solve for y. If you want to solve for x, you can use the second equation to solve for x. Either way, it's not too bad. I'll say, let's solve for y. So for our first step, we're going to use equation 1 to solve for y. That's negative 2x. We're going to need more space, so let me just go ahead and move this now. Negative 2x plus y zoom out. All right, y'all. Negative 2x plus y equals negative 11. So y is equal to 2x minus 11. That's the first step. Then once you have this, we can substitute. So we want to substitute y equals 2x minus 11. Since we used the first equation, we're going to substitute that into the second equation, into 2. And again, I'm referring to 1 and 2. I always call the first equation 1 and the second equation 2. All right, so we have x plus 3y equals 9. Then that gives us x plus 3 times 2x minus 11 equals 9. Then we want to solve this resulting equation. We're probably going to need more space, but that's okay. We'll try. Then solve. So now we'll have x plus 6x minus 33 equals 9. That's 7x minus 33 equals 9. If we add add 33 to both sides, we have 7x is equal to 42. And then dividing both sides by 7 gives us x equals 6. All right, so that's our first coordinate. X is equal to 6. Now that we have this, we know x is equal to 6. We can use that, plug it into either of those original equations to then find y. I'm just going to plug it into the original one. So we're going to use x equals 6 and negative 2x, or I'll say and equation 1 to find y again. So we have negative 2x plus y equals negative 11. That's negative 2 times 6 plus y equals negative 11. Negative 12 plus y equals negative 11. And then y would be negative 11 plus 12, which is 1. So our solution, we want to write as an ordered pair, x comma y, it would be 6 comma 1. Now we have another you try, problem number 6. We have x plus 3y equals 5 and 2x plus 4y equals negative 10. We're going to solve this again by substitution. Just looking at the equations, there's only one variable that has a coefficient of 1. That's the x in the first equation. So my hint to you, you can use equation 1 to solve for y, or to solve for x. If we take the first equation and solve for x, we have x plus 3y equals 5. So x would be equal to negative 3y plus 5, or you can write it as 5 minus 3y. That's fine too. Then when we substitute this, we're going to substitute x equals negative 3y plus 5 into the second equation. So 2x plus 4y equals negative 10. That's going to be 2 times negative 3y plus 5 plus 4y equals negative 10. And then we want to solve this. That's negative 6y plus 10 plus 4y equals negative 10. Okay. Then, let's see, we have negative 6y plus 4y, so that's negative 2y plus 10 equals negative 10. Subtracting 10 from both sides gives us negative 10y equals negative 20. And then dividing by 2, y equals 10. And then we're going to use y equals 10 to find x. We can use the first equation. So x plus 3y equals 5. That's x plus 3 times 10 equals 5. So x plus 30 is 5. And if we subtract 30 from both sides, x is equal to negative 25. The solution is negative 25 comma 10. So we've gone over this one method of substitution with a few examples here. The other method that we can use for solving systems of equations is called the method of elimination. And basically it deals with adding the two equations together, but we want to add them in such a way that one of the variables gets eliminated. You might be thinking, well, how's that going to happen? The way that the variable will get eliminated is if you have your x's, if the x's have opposite coefficients, then when we add the two lines together, the x's will cancel out. So the goal is to try to force one of the variables to have opposite coefficients, and then add the two lines together, one variable will be eliminated. All right, so the steps for solving by elimination. We're going to take our system. We want to make sure that both equations are written in standard form. So ax plus by equals c. And then you want to line up the x's, line up the y's, and then line up the constants on the other side of the equation. All right, our goal is to, for one of the coefficients, either x or y, you want to have, for one of the variables, either x or y, you want to have opposite coefficients. So you're going to look at what you have, figure out which one you want to eliminate, and then we're going to multiply the lines by a constant so that the coefficients in front of, say, x are opposite, or the coefficients in front of y are opposites. So we have to figure out what to multiply by to make the coefficients opposites. Once we do that multiplication, then we go to step 2. We add the resulting equations together. So add the x's, add the y's, add the constants, see what you get. One of the variables should cancel, and then you'll be able to solve for the other variable, substitute that into the equation, and find our solution, our ordered pair. All right, these steps are on page 63 in the book, if you want to refer back to this. Problem number 7 is a worked out example of elimination being done. So if you want to, while you're checking your notes, see another example, you can look at that example. I am going to jump to problem number 8 so that we can do the example together. So this one requires us to do a little bit of thinking ahead of time. For problem 8, we have 3x plus y equals 5 and 2x minus 3y equals 7. This is nice because it's already set up for us in standard form. And all of the x's are lined up there together, all of the y's are lined up there together. We then want to look at the coefficients for the x. So the x's have coefficients of 3 and 2. Those are not opposites. And then for the y's have coefficients of 1 and -3. Those are not opposites. But we can multiply either one line or both lines by a constant to make them opposites, okay? In theory, it doesn't matter which variable you try to eliminate. You can solve it either way, but you need to choose ahead of time which one you want to eliminate. Sometimes it'll be easier to eliminate one variable than the other. For instance, in this example, say for the y's, the first coefficient is 1 and the second one is -3. If I multiply this first equation by +3, then my my expressions with y in them, will have opposite coefficients if I multiply that by 3. All right, I would end up with, and we have to multiply everything, 9x plus 3y equals 15. And I really don't like my notation here, so let me be a little bit better about this. We're multiplying both sides of the equation by 3. So multiply this side by 3 and this side by 3. Everything is being multiplied by 3. All right, then the second equation stays the same. 2x minus 3y equals 7. This lovely thing that we have happening here is our goal. We want one of the terms to have opposite coefficients. One has a plus 3y, one has a minus 3y. This is the goal. We were able to do that by just multiplying one of the equations by 3, the first one. All right, once we get to this step, one of our variables has opposite coefficients. Then we get to the addition part, we add. So if we add these two lines together, 9x plus 2x would give us 11x. 3y plus negative 3y would give us 0y. And 15 plus 7 would give us 22. So this is nice. Once you have those opposite coefficients, when you add the two lines together, the y's go away, and we just have 11x equals 22. That's easy to solve. X is going to be equal to 2. And then from this step, it works out just like the other one. Once we have x, we can then use x equals 2 to find y. You can plug it into either equation. So I'm going to go 3x plus y equals 5. That was the original equation. So we have 3 times 2 plus y equals 5. 6 plus y equals 5. And then y would be equal to 5 minus 6, which is negative 1. So our ordered pair is 2, negative 1. All right, boom. So in problem 9, this is an example where we would have to multiply both of the equations. Okay. When we look at our coefficients for x, we have 3 and 5. When we look at the coefficients for y, we have negative 4 and 3. Those aren't opposites. So either is easier here, so we can just pick. In order to eliminate the x's, we need the coefficients to be opposites. Right now we have a 3 and a 5. How are we going to get those to be opposites? Multiply by the, go ahead. Somebody had a
I was going to say multiply by 5, then for the second one, multiply by 3.
Almost. We need the signs to be opposite also. So make one of those negatives. But she has the right idea. But that's the right idea, Cameron. You're going to multiply the first equation, and I'll write it out in words. We can multiply the first equation by 5. That's the second equation's coefficient. And then multiply the second equation by negative 3. And I'm doing negative 3 because one has to be positive and one has to be negative. Okay, let's write that out. So I have 3x minus 4y times 5 equals negative 9 times 5. And then 5x plus 3y times negative 3 equals 14 times negative 3. All right. Then let's simplify. So the system becomes 15x minus 20y equals negative 45. And then negative 15x, very good. Be careful with your signs here. Minus 9y equals 14 times negative 3 is negative 42. Once we get to this part, those x's have opposite coefficients. Life's great. Then we can add the two lines together. So we get 0x minus 29y equals negative 87. So we get negative 29y equals negative 87, and then dividing both sides by 29. 87 divided by 29 is 3. Thank you. Then from here, we use y equals 3 to find x. You can use either equation. 3x minus 4 times 3 equals negative 9. That's 3x minus 12 equals negative 9. Then adding 12 to both sides gives us 3x is equal to 3. And finally, x would be equal to 1. So our solution here is 1, 3. All right. This problem is obviously set up nicely for us to use substitution, because if you look at the second equation, y is already solved for us, but we're specifically asked to use elimination. So I at least want to get you started on this one to show how you would use elimination. First, the equations are not in standard form, so we have to put them in standard form. We can multiply that second equation by 4 to get rid of the fractions. And then we would have 3x minus 4y equals 12. And 4y equals 12 minus 3x. That's if I multiply all of this by 4, just to get rid of the fraction. All right, that's the first thing. Then the second thing, we have to put this in standard form. The first equation is 3x minus 4y equals 12. For the second equation, if I add the 3x to both sides, okay, we get 3x plus 4y is equal to 12. This is an interesting case here. Interesting case. All right, let's see what we end up getting. Our y's have opposite coefficients, so we don't even have to multiply anything again. We already have opposite coefficients for the y's. That's good. Then when we add, we get 6x plus 0y equals 24. So 6x equals 24 and x equals 4. Using that, we get for y, 3 times 4 minus 4 times y equals, my 4's and y's look alike. 4y equals 12. So that's 12 minus 4y equals 12. Subtracting 12 from both sides gives us negative 4y equals 0. So y would be equal to 0. And our solution here would be 4, 0. I believe it.